let's start our webinar today. 6 p.m. We have a very interesting topic. What is Transonic Buffet? We will have an introduction to supersonic flows with an example solved in ANSYS Fluent. Before we start, I would like to ask you to turn off your cameras beside the speaker, turn off your sound, and write the questions in the chat. We have a chat function. And we also are running some surveys in the chat, so you can also give your vote and give us a little bit of understanding of your background so we can shape the webinar into one or another direction. And I would like to start with a brief introduction of WiredWhite, of our platform, what we do and why we do it. So basically, we are a network of engineers. We envision ourselves as a network and a platform that guides individuals throughout their engineering career, like on the customer side and on the engineer side, on the partner side. And we bring customers and engineers as partners together on our platform, and we provide all the necessary tools to collaborate and to work together, enabling global cooperation between customers, students, and partners, technical experts, and engineers. And why we do it? Because we see our mission in acceleration and optimizing the diffusion of electrification worldwide. We strongly believe that it is possible through enablement of this global sort of cooperation and knowledge sharing of what we are doing with our platform. And this became our vision, and this is what we believe is our contribution to that. And today's speaker is Cesar Jimenez Navarro. Cesar is aerodynamics engineer at Airbus Defense and Space in Getafe, Spain. He contributes to design and develop the next generation of military aircraft, and he holds a PhD in fluid mechanics from Institut National Polytechnique de Toulouse. His doctoral research is advanced and in understanding of transonic buffet phenomena and in the morphing wing concepts, and also in the modeling of turbulences. Alongside with his research and industry work, Cesar is deeply engaged in teaching and knowledge transfer. He lectures in thermodynamics and fluid mechanics at the University of Telemani in Andorra, and he has created widely used online courses on Python-based CAD automation and scientific visualization. And his teaching journey is also included roles at INPT in Toulouse and University of Linköping in Sweden, where he mentored students in CFD and aerodynamics, and his expertise is spanning programming and CAD and CFD, since he brings both technical deepness and also passion for education to his professional endeavors. So I would like to welcome our speaker today, Cesar, and the ball is yours now to start with the interesting stuff.
Okay, thank you so much for the kind introduction. I think I will share my screen so we can get started. Okay, screen. Okay. Okay. Can you confirm that you can see the screen?
Yes, we can.
Okay, that's perfect. Also my marker. Great. So welcome everyone to this seminar. I've prepared this talk in order to give you an introduction to supersonic flows, to let you know like which are its fundamentals, why they're like so critical. And I hope that at the end of this talk, you have a better understanding of it. And I have prepared the following topics, just like a brief introduction to what the supersonic flows are. Then we will cover the fundamentals, and then we will practice a little bit by solving the analytically and through simulation the flow over a supersonic wedge, which is a well-known study case in this kind of flows. Then we will tackle the interaction between shockwaves and incoming boundary layers. And then we will see a major supersonic instability that occurs in wings at the transonic region, right? And we will finish with conclusions, takeaways, and any questions that you want to ask me. So let's begin. As you already know, the aerospace sector plays a big role in today's society and the economy. And this is thanks to its key characteristic, which is speed. However, at these extreme conditions, right, the aircraft or any vehicle moving at over the speed of sound affects heavily the media through which it moves, right? And this raises the compressibility effects. For now, I don't want to get too technical over it, but just to make emphasis on the fact that these compressibility effects govern the physics of this flow. So it is key to understand these flows in order to manage them. Let's take a quick look back in history, because maybe some of you already know this or maybe not. The first manned supersonic flight was in the late 40s, so in 1947, when the Bell X-1 broke the sound barrier. But then it took nearly 20 years to make this technology ready for the general public, right? To make it commercial. Why is this? Because dealing with supersonic flows, it is incredibly challenging. And having an object or a vehicle that moves such a speed through shock waves, it is incredibly expensive from the field or the energetic point of view. That's why we haven't seen lately so much of supersonic aviation. There are some startups that want to develop new supersonic aviation concepts, but I anticipate that the flight tickets won't be cheap for this exact reason. Also, regarding space exploration, this is also another sector where compressibility effects matter. And this really began around the 60s with the Project Mercury, which was the first human spaceflight program. And in these conditions, you are not only dealing with compressibility effects, but also with reactive flows. Because at some beyond some temperatures, the air stops being air and it creates new species, and you need to take into account these new chemical reactions in order to be able to predict accordingly the aerodynamic properties of these vehicles. And even though it seems that we have achieved a lot in these 60 to 80 years of aviation, there are still like many challenges that are still unsolved. One of them is prediction. At the moment, there is no unique methodology that allow us to predict how supersonic flows behave. Then supersonic flows are normally linked with unsteady effects, which are very detrimental for the performance of aerodynamic components. Also control. There is a huge lack of effective shock control strategies nowadays. And even though if you come up with the right one, you will always have to negotiate through design trade-offs in your final design. So there is there will be never a perfect solution for your problems. So now we're gonna jump into physics, right? So we're going to start with the fundamentals of these compressible flows. The first thing that we need to understand and become familiar is the speed of sound, which this is basically the speed at which the perturbations in forms of pressure wave travel through gas, right? Or like at the speed of which these perturbations propagate in a given media, which is in the case of gases it is a function of the ratio of the specific heats, the specific gas constant, and the absolute temperature of the gas. So the higher the temperature, the faster these particles move, and therefore you will have a larger speed of sound. Another key metric to be familiar with is the Mach number, which is the non-dimensional ratio, which is calculated with the velocity of the vehicle over the local speed of sound, right? So if we have a Mach velocity of 1, that means that we are moving exactly at the speed of sound. If we have Mach 2, we are moving at twice the speed of sound, and so on. And through this number, we can classify some of these like the regime of the speed regime of some vehicle. So when we have incompressible flow, this is below Mach 003. We can have here UAVs, gliders, helicopters, or small or light aviation. Then beyond 0.3, we have subsonic flow, which can be slightly compressible. So here we have typically military transport aircraft and almost private jets. Here we have the transonic flow, which there is no like a clear boundary. It normally starts around 0.8 up to Mach 1.1. Then we have a supersonic flow, which is typically normal 1.1. This is up to 5 or 6 when these chemical reactions start to happen. So in supersonic flow, we normally have fighter jets, supersonic aviation, or also military vehicles. And everything above Mach 5, Mach 6, again, there is no a clear boundary, will be considered as hypersonic velocities. So why the Mach number is so important? This is because the Mach number has a key role in the flow dynamics, right? Because it changes. So because these dynamics change abruptly depending on if the flow is subsonic or supersonic. So let's start with the subsonic regime. Let's assume that we have an object moving at the speed which is lower than the local speed of sound. As this object advances, it will send information upstream in form of pressure waves, and therefore the incoming flow can sense this object, and therefore it can go around it. Okay. However, this is not the case in supersonic regime, because when we have an object which travels faster than the speed at which information propagates, basically the flow will not detect the body unless it abruptly hits it, right? So what occurs is that the propagation of this information doesn't travel upstream, and then the flow goes to wherever speed it is here, down to 0, right? Because it's we know that in an aircraft surface or in object surface, the velocity is 0. So because of this abrupt change, we have a very strong reaction, which is known as a shockwave. And now it's time to introduce our next topic, which is shockwave. This is what we're going to be dealing with throughout the whole presentation. And basically, a shockwave is a thin region formed by a succession of compression waves caused by these disturbances that move faster than the speed of sound. Which is the effect on the flow that it really has physically? So let's assume that we have a flow that moves faster than the speed of sound. This is Mach larger than 1, and then it is abruptly slowed down by the presence of a normal shock, and therefore is brought back to subsonic conditions. Well, because of this compression, what occurs is the pressure rises abruptly, and also the density and the temperature, because the gas is suddenly compressed, and therefore what happens is that the Mach number is reduced. It loses velocity. We are dropping total pressure, which decreased due to these irreversibility losses. And then it is important to understand that this reaction is so quick, so sudden, that there is no heat exchange with anything else, right? So it is an adiabatic flow, and therefore total temperature and stagnation enthalpy remain constant because of this. And because the temperature has increased, we have converted mechanical energy into thermal energy. There is also an entropy rise. Now, we're going to apply what we just learned through a very simple case, which is the supersonic wedge. So this supersonic wedge is the simplest case of shock forming around a geometry. What we have, it's a supersonic flow, which encounters a wedge, encounters an object, and therefore a shock wave is formed because the information cannot travel upstream. Here, well, I think before going any further, what we have to know now, it's to understand which is the supersonic response to a compression or an expansion. When we have subsonic flow, right, because we have to fulfill continuity, right, the mass cannot be destroyed. Given in a control volume, the product of density times velocity times the area has to be constant, right, to ensure this mass conservation. So what occurs? If in a subsonic flow we compress the flow, that means that the area decreases because of the density is constant. The velocity has to increase in order to make this product constant, right? So you can do like a very quick test just by blowing the candles in a cake. What you do is like with your lungs, you create a high pressure reservoir in your mouth, and then when you close your lips in order to blow, what you're doing is you are reducing the cross-section area, and therefore you accelerate the flow passing through your lips. However, this is not the case in supersonic flow because the governing equations flip the sign when Mach is higher than 1. Which are the physics around it? Well, as I already explained before, through a shock, what occurs is that the pressure increases sharply, and therefore also the temperature and the density, because the gas is squeezed. But because because of the process is so quick, right? We have an adiabatic process, and therefore the total enthalpy has to remain constant. So this is the total enthalpy, which normally is a function of the internal temperature and then the velocity. So if this magnitude has to be constant, and we are increasing the temperature, the only physical mechanism to keep the total enthalpy constant is by dropping the velocity, right? So we are converting we are converting kinetic energy into thermal energy in this process. Also, a very interesting relationship to study this dependency is the isentropic flow through an nozzle, where this equation what relates is the change on cross-sectional area, the Mach number, and then the variation of the speed. So if we are in subsonic regime, this term will be negative, right? So these terms will have opposite effects. If we reduce the area, we increase the velocity, and so on. But in supersonic regime, when this Mach number is larger than 1, these two derivatives will go in the same direction. If we increase the area, we increase the speed. Okay. Now that we have understood this, now we're going to see like how the supersonic flow behaves in a compression corner in an expansion phase. So a compressor corner is when the flow impacts a concave corner. This is basically when we have a geometry which is deflected a given angle, and therefore as a consequence a shock wave is formed. Initially, if we decompose the flow with the normal component to the shock and the tangential component to the flow, we can get the following relationships. And here it is important to know that the tangential velocity over the shock, it remains constant because only the normal components get accelerated. So if we use our trigonometry knowledge by keeping this magnitude constant and reducing the magnitude of the normal component, what occurs is that we have a resulting velocity which is lower than the initial one, and also has been deflected in one direction. And this direction is the same angle as the deflection over the compression corner. Now we have the opposite case, right? We have a supersonic flow that what encounters it's a convex corner. This is an expansion. So what occurs is that once again the tangential velocity is kept constant, but because the supersonic flow is expanding, it increases. It increases its normal velocity, and therefore the total velocity also increases. Now we're going to see like how we solve analytically these equations. Please don't hate me for this slide because there are like many equations that might not be super appealing to most of you. These are the equations that are solved that are used to solve oblique shockwaves on compression corners. The first one is the so-called theta beta Mach equation, because it establishes a relationship between the incoming Mach number, so Mach 1, the deflection angle, which is theta, and then also the shock angle, which is beta. Then we have the Mach equation, which basically allows us to compute the Mach number after the shock as a function of the incoming Mach number, the shock angle, and also the angle of this obstacle. And then we can also compute the strength of the shock by measuring the ratio between the pressure after the shock and before the shock. So the higher this ratio is, that means that the shock wave is stronger. Now we have the Pratt-Meyer expansion fans, which are computed by using this equation. And this equation, what it does, it computes the angle that a supersonic flow has to turn in order to reach a given Mach number starting from 1. Okay, so if in this equation we substitute Mach 1, so the Mach number for 1, this value will be 0 because the flow is already supersonic and it doesn't need to turn to reach this number, right? So the larger this Mach number is, the larger this angle is going to be. So how do we use it? So first of all, we need to compute the turning angle that we need to have for having the Mach before the expansion fan. Once we have this angle, what we have is another expansion, which is the first theta 1 plus the theta of the obstacle, and then we get the turning angle of the Mach after the shock wave. And now what we do is we solve this equation substituting V2, and then we solve this equation for Mach number, for the Mach number, and we will have the Mach number after the shock. And then the rest, the only step left will be to compute the rest of variables using the isentropic relationships because we are in a diabatic flow. So now let's put all this in practice. Let's solve an exercise. So we have a supersonic flow. In this case, is flying at Mach 2. And what occurs is that it encounters a sharp wedge with a deflection of 10 degrees, right? So we are asked to compute the Mach number after the shock, after the wedge, and assuming that the air behaves as an ideal gas with a gamma equal to 1.4. As well, let's analyze the case. Basically, the flow is coming in this direction from left to right without any kind of deflection. And what occurs is that it is deflected 10 degrees upwards, right? So what we expect to have there? We will expect to have a shock. And then once it reaches the end of the wedge, we will have the opposite effect. So as a consequence, we will have the following system in which we'll have an oblique shock departing from the starting point of this wedge, and then we will see an expansion fan because the flow is also deflected minus 10 degrees, right? So we have a compression and then an expansion. Using the equations that we have seen in the previous slide, we can compute the beta angle, so the shock angle, as a function of theta and the Mach number. The way you solve this is typically using a numerical solvers. Like in this case, I use Python, and depending on which is your initial solution, you will converge towards the weak solution or the strong solution. But in this case, we know that the shock is attached. I will cover that later on, and we will take the weak solution for this case. Sorry. Once we have beta, we have also theta and Mach and an incoming Mach number. We can solve to get the Mach number after the shock, and we just simply substitute terms and compute the Mach after the shock, right? So we move from Mach 1 equal to 2 to Mach 2 equal to 1.64, right? So here we can already see that the flow has been decelerated by the presence of this oblique shockwave. Now is when we go to the expansion fan. So first of all, we know already the Mach before the expansion fan. So by solving this equation for V2, we get that the expansion angle has to be 16.06 degrees. And then for the shock, so for the Mach number after the expansion fan, we know this angle has to be the previous angle plus the turning angle, which is 10 degrees, right? So we just add 10 degrees in this case, and then we go back to the same equation. In this case, we already have this value that we have already computed before, and then we have to solve this equation for Mach 3. And we solve this equation, and we get that the Mach after the shock and the expansion fan is 1.99. As you can see, we have done the process and the inversion. So we have done a compression and then expansion. We can see that we don't reach the same value, right? It was initially 2, and now it's 1.99, right? So reflecting that here, we have lost this mechanical energy that has been converted into internal energy. Okay, so now that we have solved this exercise analytically, we're going to solve it numerically by using a commercial software, which maybe most of you will know, ANSYS Fluent. So the steps for solving this equation is, first of all, create the geometry, create a design mesh in order to capture the main flow features, simulate the flow, and then post-process the results. Try to understand what we are looking at. And I think here I will quit the presentation. I will move to the workbench. Okay, so maybe if some of you has already used ANSYS workbench, maybe you're familiar with this setup. So first of all, we'll have the geometry block. So let's open it here. Okay, so you can see it. So basically, this is the domain that we have created. So this is the wedge, the wedge that I have just specified. This angle with respect the x-axis forms 10 degrees, and then it goes flat again. So what I've done is I've created 2 sketches. One is to create the computational domain, the computational control volume, and then what I've done is I created a secondary sketch in order to split the first one. And why am I doing this? Well, first of all, we don't need we have to understand in CFD we need to put the cells, like the computational cells, where they are really needed. And they are really needed where you have to solve features that have many gradients or need a very fine resolution, right? Which is the case of a shockwave. So by doing this, what we can do is we have 3 separate regions from which we can specify different volume sizings. We will see that later on in the mesh. So I created these sketches. I create a surface from this sketch, and then I use the sketch tool in order to split the face. Okay, then what we move is we will go to the mesh block. Oops. Okay, and then for the methods, well, I've loaded this geometry into the ANSYS measure, and then what I've done is I've created 3 sizings, right? One for the first phase, which we don't really need a resolution because, as we already know, we're in supersonic flow, so whatever happens here won't affect upstream, right? So you don't need to have a lot of resolution in this area. Then we have the area where the shock occurs, right? We're here. We need a very fine resolution. Oh, also, I forgot to mention, how did I split? Like, how did I choose these angles to split domain? Well, basically, before we have already solved these analytical equations, right? So we know which is the angle of this shockwave, right? So what I've done is I did a cut slightly upstream than the shock, and I created this line which departs with an angle of 40 degrees. Let's go back to the solution. Sorry, right? Because we know that the weak solution is 40 degrees. So I created this line, and then after the shock, what I've done is I created another line with an angle which is 10 degrees less, for instance, right? So like this, I could dimensionate, like I can orient in a realistic manner the region where the shock is going to be captured. Then we have also the third sizing, which the mesh resolution is lower than this one, but larger than the first one. And also I've created some edge sizing, because what we need to do is we need to also capture properly the flow features around this corner. So we have here a bias factor in order to concentrate the cells around the start of the wedge. Then we have a secondary sizing with fine cells here and fine cells here, and then the same for the upper section, right, which is to concentrate cells in the turning regions. So if we do a mesh, so if we complete the mesh, we have the following grid with the features that I have already introduced. And then once we have the grid, what we need to do is go to Fluent, okay, and then solve the case. So first of all, because we are solving a compressible case, right? The density-based solver, it's mandatory because we need to solve the pressure density coupling equations. Then in models, we need to turn on the energy equation, because these compressibility effects need the information provided by the governing equations by the governing energy equations. For viscous, for this case, we are solving implicit interaction, so we are not gonna use any turbulence model in this case, because we don't have any boundary layer to resolve. Then for materials, I am using a regular air, and now we are going to talk about the boundary conditions, right, which are quite important. Let's go on display them. So first of all, we have in the surrounding edges, we have a pressure far field boundary condition, which is a non-reflective boundary condition, and this is like quite ideal for solving supersonic flows. Then we have a symmetry condition because we are solving. Let's go quickly back to the presentation. Oops, sorry. Because we are solving, we don't need to solve the whole wedge, right? So just by solving, we know that we're going to have the same flow features above and under the wedge. So for that reason, we are using symmetry, and therefore we are saving the computational resources by doing this. Then we have the wedge, which is set as a wall, and then we have the bottom, which is the rest of the surface until the end. Okay. Sorry. So these are the main boundary conditions that we are going to set. Additionally, well, I'm going to display already these 3 lines, because these 3 lines, what they are, they are like sensors, they are monitors that I will be later on using through simulation in order to assess if my solution is converged or not. Okay, how do we do this? Well, first of all, here in report definitions. Okay. No, sorry. First of all, you need to create the lines. So at the end, in results surface, you can create lines with the coordinates that you wish. And once you have created these 3 lines, you can create a report with them. So basically, here in this report, line 1 pressure, what I'm showing is I am doing the area weighted average of the static pressure across this line, and then I'm outputting a number that I'm controlling through the simulation. And then I have 1, 2, and 3 monitors. Sorry, 3 report definitions. And then here I am creating a report plot where I am showing the evolution of these metrics. We will see later on what this really means. Then regarding methods, so we're using an implicit formulation. We're using the row upwind scheme method, like a row upwind scheme for the flux calculation, which is a pretty standard method for shocked flows. We got the gradients. We're using the Green-Gauss node-based gradient, and then for the fluxes for the flow, we are using the 3rd order massless beam. I don't want to get too deep on this because this is an introduction to supersonic flow, but maybe like in another different seminar, we can cover solution methods or numerical methods for compressible flows, but not in this one. Then what we will do is we will initialize this case by using a hybrid initialization, and then we will run it. I'm not going to run it here because I've done already like some tests this weekend, and it takes around 20 to 30 minutes to run this case, and that could be like quite endless. So I have already prepared some slide which already like shows the process. Okay, can you pop out 1 second? I just to hide this. Okay, let's go back to the presentation. Great. Okay, so we have already explained this, the boundary conditions. We have already covered the volumetric mesh. I have already explained which are the solver settings that we have set in Fluent, and then we press the running button, right? So how long do we need to run this simulation? So first of all, we have a residual target around 1 to the power of -3. Then we have the settlement of the pressure distribution along these 3 lines that I have introduced before, which are basically these 3. And here we have the evolution of the pressure over these lines throughout the iterations, right? So basically what we need to do is we need to run this simulation long enough until we reach convergence, until we reach a steady value of these metrics. And regarding the control, and also we are also monitoring that in the final solution we don't have any kind of strange features in the flow. So if we will have stopped a simulation, like let's say around 1000 or 2000, that might be like not good enough, because you can see we have like many spurious effects throughout the domain. It is really above 2500 iteration where the solution seems to be completely converged. And now that we have already solved this flow analytically and numerically, we can compare the results. Surprise, surprise, there's almost like no difference. Here we have the matrix that we have computed by using theory, and here by CFD. So the first number is the ratio of the shock before and after the oblique shock. Then here the pressure jump, and then the temperature jump. As we can see, the equations that we have solved previously lead to a very small difference in the metrics. And then we have a very similar behavior in the expansion fan, where we have almost a 20% difference. So as you can see, like with analytical equations, you reach basically the same values as CFD. And what happens with the shock deflection angle? So the shock deflection angle, it's this beta, which is the angle that the shock forms with respect to the horizontal axis. And because we know the location of these points, we can compute the delta x and the delta y, and therefore we can compute this angle using the inverse tangent of these deltas. So for this case, we have solved only one case. This is the case that we have displayed before. So for a case of 10 degrees deflection angle Mach equal to 2, we will have a shock angle of 40. But if we do like different CFDs in different conditions, and then we compare with the analytical solutions, what we see is that there is a really good agreement, really good match between theory and numerical methods. And one thing that you might be wondering, well, if you have fully understood what we're talking about, that you were able to cope up with the base of the talk, what you will see is that there is a limit solution for each Mach angle. That, for instance, like for Mach 2, the maximum deflection angle that you can have is around 22 degrees. Why is this? Why you cannot have a deflection angle with 30 degrees at Mach 2? Well, this is because these equations work only when you have fully attached shockwaves, right? This is a shockwave that forms exactly at the starting point of the wedge. If you have a larger deflection angle, what occurs is that you will have a detached shock in front of it, and that leads to way more complex phenomena that we will see in the next section. So conclusions of this exercise is that we have confirmed the physics of these supersonic flows. That when a supersonic flow encounters an obstacle, it forms a shockwave around it, and an important discontinuities in the flow properties. Then the magnitude of the Mach number and the angle deflection governs the shape and strength of the shockwave. And also, we never should underestimate analytical, theoretical, or empirical approaches, right? Because they can save us a lot of time and a lot of money. Just to put some numbers in this case, setting it from the beginning until the end in CFD, it took me around 45 minutes. Whereas the theory running that equation is around 1 millisecond in a regular computer. And then for CFD, you will need like more budget, more skills, and then you will have the same level of accuracy, right? So my message to you here is like, please never underestimate theoretical approaches. Now we go to the next topic, which is the interaction between boundary layers and shockwaves. And I realized that I haven't introduced what a boundary layer is in this talk, so I'm gonna just like improvise it here. Basically, we know that the flow in a wall or in the wall of a vehicle or in any solid wall has to be zero, right? Because the walls do not move with respect to each other. And therefore, the flow particles that are in contact with the surface are steady, right? So the velocity here is 0. So what happens that here a boundary layer is a region of the flow which whose velocity evolves rapidly from 0 up to the free stream velocity, right? In this case, we have a supersonic flow. So basically, this is what a boundary layer is. So this region of high velocity gradients. Now let's assume that we have a shock wave that what does is bringing the flow from supersonic back to subsonic. What occurs here is that we know that after this shock, we will have subsonic flow, and therefore what we can do is we can look for a trace of where this change occurs, which is known as the sonic line, right? So this is the division line between supersonic and subsonic flow. Here we have supersonic flow. Here we have a supersonic boundary layer, and here we have a subsonic boundary layer, and here we have subsonic flow. As we already seen before, in supersonic flow, when you perceive a deflection, you will always have a shock, right? So what occurs here is that we have bended the sonic line. So as a consequence, the reaction is to release an oblique shock wave, and this oblique shock wave increases the pressure, reduces the velocity, and therefore it tilts once again the sonic line. So you'll have this reaction over and over and over again, forming infinite shock waves that will always end into a normal shock and bringing down the flow from supersonic back to subsonic. And let's analyze the pressure, the pressure changes across each region. So let's consider the so-called invisible regions where the viscous effects are negligible. So what occurs is that the flow will not sense anything, and then suddenly, because of the presence of a shock, boom, you will have a sharp rise in pressure. But as we can see here we don't have the same effect, right? Because we have a viscous region. What occurs is that this information, this pressure rise, has been propagated through the subsonic boundary layer, which allows the flow to travel upstream the shock, and therefore increasing gradually the pressure before the shock's location. This is what is called upstream influence, and therefore and afterwards we'll have the slow recovery, in which later on, far downstream, the flow will reach the equilibrium into a fully turbulent boundary layer. We can also have the case where the shock abruptly is strong enough to separate the flow, and it will form a separation bubble. Sorry, that can turn the flow upstream and create this secondary recirculation region. Also here, the pressure distribution will be different as the previous case, because what we are doing is we are crossing two shocks. So we are crossing, first of all, an oblique shock and then a normal shock. So first of all, we'll have a slight pressure jump and then a bigger pressure jump, because the second one is normal. And always, a normal shock is always stronger than an oblique shock. But here, thanks to the fact that we have crossed an oblique shock before of a normal shock, the total pressure is not so abruptly dropped, right? So as a consequence, we have a gain in the total pressure after the shock system, right? This is what supersonic intakes try to do before bringing the air towards the engine, which needs to be subsonic. They decelerate the flow through several oblique shocks in order to give the optimal conditions to the engine. Also, we can have this scenario where the flow detaches, but what occurs here? Here, the flow is very close to Mach 1, right? And what happens if, for some reason, there's a turning in a direction? You might be already familiar with this shape, because this can be an expansion fan. And this expansion fan will mean that the flow will accelerate once again to supersonic conditions, and then it will form another supersonic tongue after the main shock system, and can even help the recirculation bubble to touch again. Then, sorry, I'm seeing that I might be like tight on time. I have like 10 minutes, so I think I might have to rush a bit. So yeah, so we have also the case where we have a compressing corner with a bonded layer, this is different with what we have seen in the previous case with the supersonic wedge, where we were neglecting the viscous effects. But in this case, when the shock finds the corner, we might have a thickening of this bonded layer, and then as a consequence, we will have the formation of the shock because of the same principles that we have seen in the previous slide. If the interaction is strong enough, what can occur is that the flow separates and a free shear layer forms so over this compressor corner. And once it reaches again the compressor corner, the flow changes once again the direction, forming a secondary shock, which is known as retachment shock. So we'll have the first oblique shock, and then because of the separation, we will have a secondary shock known as retachment shock. Now we're going to switch to the latest topic in the presentation. I hope that I will have the time to present it, like in 8 minutes. So the Transonic Buffet is a well-known study.
No worries.
Okay. I think with 8 minutes I can be good. I think it's the perfect time for presenting this. Okay, great. So okay. So the study case that you're looking at the moment corresponds to the flow over the B2C wings under heavy buffet conditions. This buffet instability occurs in wings transonic speeds when critical conditions are met in terms of Mach number and angle of attack. The origin of this unsteady instability is linked with the unsteady nature of these wake instabilities, and also the interaction of the shockwave with the incoming bonded layer, right? The so-called shockwave-boundary interactions that we have seen in the previous section. And it is also said that the SBLI, the shockwave-boundary interactions, are the biggest obstacle for the development of supersonic aviation, since there isn't like enough knowledge of how to deal with these super complex interactions. So now let's take a look on the lateral side of the wing. As we have already seen, the buffet consists in a self-sustained cycle, which causes the shock to move back and forth with certain frequency and amplitude. But here we ask ourselves, okay, but why this is bad? Like why we don't want to have this situation in a real scenario? Okay, to answer to this question, we need to understand that the normal force with respect the flow direction, known as lift, is generated by the pressure difference between the upper and lower surfaces of the wing. So if we do, okay, my slides are not working. Okay. Oh, fine. I cannot pass this slide. Oh wait. Okay. Now it works. Okay. If we do a cut over in the midsection of the wing, we can plot the pressure distribution across it, and this gives us information of where, like the magnitude of the lift and where it is generated, which is indicated by the difference between the upper and lower curves. Here what I displayed is the shockwave, sorry, the pressure distribution in two key moments. In blue, we have the case where the shock is at its most upstream location, and then in red, we have the case where the shock is at its most downstream location. And the way to easily spot the presence of a shock is to look for this sharp increase in pressure. Please note that this is reverse, which is indicated here and here. And as we can easily visualize, is that for the blue case, there has been a substantial loss of suction, so a substantial loss in this area caused by the upstream excursion of the shockwave. Because this stability occurs is stationary, it causes a force variation which occurs at the same frequency of the buffet, and causes like force variations which are proportional also to this to the distance traveled. In this case, it's around 30% of the median value, which is a very that's like a very high value, and therefore this causes very strong and very undesired vibrations that force the aircraft manufacturers to limit the flight regimes of the aircraft. Here we have it's a typical representative flight envelope of an aircraft, and normally in red you have the regions where your aircraft should never be in terms of the load factor and the velocity. So typically, as we have seen before, this flow instability is caused when critical conditions are met of velocity and incidence, angle of attack, and therefore that's why it normally limits the actuation of the aircrafts in these regions. So as you can understand, it is key to understand the physics in order to, first of all, avoid running into the situation, or if you do, try to mitigate this effect. And that's why there are like many studies trying to understand this physics and develop flow control methods. What we are looking at, it's an experimental visualization from my colleague Alessandro Daguano, already doctor from TU Delft. Sorry, the video stopped. I don't know why my presentation is being a bit messy today. Okay, fine. I don't know why it's okay. Well, oh my gosh, like what is going on with the video? It was working perfectly before. Sorry guys for this. No, okay, the video stopped. My presentation is completely blocked. Oh, wait. Whoa. Whoa. Are you guys? Can you guys hear me?
Yes, we can.
Yes, I'm not sure. Like, I don't know what happens to my computer. Like, okay.
Sorry, that was the slide number 39, right? Or 37? 39.
Yeah, 37. Yeah, sorry. I'm very sorry because I don't know what is happening to my computer at the moment.
No worries. No worries. Can you guys see my screen?
Yeah.
Or is it working now, Cesar?
No, it's completely frozen. Okay, so maybe like we can proceed like that. I honestly don't understand what happened. Okay, so can you go to the previous slide, please?
Yes.
Yeah, so I was mentioning that this is an experimental visualization from my colleague from TU Delft, right? And here we can see is the real physics of the phenomena, right? So we can see like how the shock wave moves back and forth, and then how the flow after the shock alternates between a fully separate and attached state. However, normally having real measurements or accurate measurements on these experimental setups can be quite challenging because we need to actually introduce probes. We need to actually go into the flow and measure the properties. And normally this can cause some disturbances and inaccurate measurements due to the perturbation. And now can you go to the next slide? And this is exactly where computational fluid dynamics excel, because we are modeling all this numerically. We have access to all the data in the flow, right? Because we have discretized all our domain into small control volumes, and then we can access exactly to the data. However, we are using models, and as I said before, everything can be. We need to know the limitations of each model, and therefore we need like a strong interaction between experiments and CFD in order to really understand the real dynamics. Can you go to the next slide? Perfect. Now here in this section, in this part, I will stop the video to just to mention the flow properties that we are looking at. First of all, we have a lambda shock, right, which is a typical sign of shock-induced separation. You should really like recognize the pattern from the slide about Shockwave-Boundary Layer Interactions that I showed before. We have a normal shock that causes a pressure rise in the model layer, and then as a consequence, we have an oblique shock that terminates in this normal shock, and this is like a very typical sign of shock-induced separation in transonic flow. Can you press twice the slide? Another one. Perfect. Here, what I display is the sonic line, which is the boundaries between the subsonic and the supersonic region. And then press once again. Perfect. Beautiful. So what we are having here is that near the leading edge, we are having a supersonic, a subsonic compression that accelerates the flow from subsonic to supersonic. And then once it reaches supersonic conditions, this is Mach 1 in the sonic line, the flow is further accelerated by the supersonic expansion, and this acceleration is sustained until the flow encounters the shock, and then is brought back to subsonic conditions. However, due to the curvature effects, due to the rise of pressure by the shock presence, and the flow instability is coming from the wake, this causes a massive separation, and that's why we can see the alternating pattern between a fully attached and a fully separated flow. Just to conclude this summary, just to mention that this condition only appears in wings of design conditions. So a well-designed wing operating at the right design conditions will never experience transonic buffeting. Okay, so now we can go to the conclusions directly. Okay, yeah, 2 more slides. Perfect. Okay, so conclusions from this seminar: supersonic and transonic flows are governed by compressibility effects and dominated by shock waves and expansion. The simple cases can teach us the fundamentals to introduce us to this complex world, as we have seen in the supersonic wedge, where we could really like understand the fundamentals of oblique shocks and expansion fans. Then the next point, interactions make it complex because we have seen initially how the shocks work in inviscid regions. When we add viscosity effects, that can cause way more complex effects that need to be fully understood and carefully studied in order to mitigate the harmful effects of these interactions. Then the next point, instability is a limit performance, and Transonic Buffet is a clear case of it, which it is typically the key limiter of these flight envelopes. And then the final point, and then the engineering impact is huge, because the design of these high-speed mechanisms work. So because of the high complexity of this supersonic flow, it is key to understand how they work in order to counteract and design vehicles that can mitigate or can deal with these very severe and harmful effects. And this is everything from my side. I hope that you have enjoyed the talk. Sorry for the last 10 minutes because they were quite hectic. I had like many technical issues. But if you have any questions, I would be very happy to answer them.
Thanks a lot, Cesar, first of all, for that
Thank
amazing webinar, and the speech was quite insightful. So I think we have a couple of questions raised in the chat. I'll just switch to them. We have, I think, a couple of raised hands during the webinar. So maybe this is the first one. Is gonna be what factors make shock boundary layer interaction more complex? The question from Genesis.
What factors? I will say definitely like the Reynolds number. So normally, typically, the more turbulent a flow is, that leads to way more, let's say, way more complex turbulent structures. And yes, I would say that when the initial forces are dominate over the viscous ones, yeah, because therefore you have like very complex interactions with the larger structures, the small ones. Yeah, that can be quite messy to study. Yeah.
Thanks for that. I hope that's answering the question, Genesis. If not, then just follow up with one in the chat. And the next one would be from Pau Mondeno. He's asking about, are there any active flow control methods being studied to decrease this effect of the transonic buffet?
Yeah. So there are like some of them that have been studied. It's a shame that I didn't include some of them in the presentation, but as you can see, like it was quite lengthy already. One of the most effective ones are blowing on suction, because with them you can really control what happens near the wall. But unfortunately, they have not been tested, or they are not like mature enough to really solve an industrial problem, right? To have it installed into an aircraft and make it cost effective. Because you could install it, but that will require a lot of maintenance. Then you will have to bleed energy from somewhere else, like probably from the engine, or to activate these devices. So I would say active flow control is really complex. Normally passive ones like vortex generator and so on, it's something that it is installed nowadays in aircraft, and they have shown to be like quite effective. But active, so far, I am not aware of any technology which is like widely used.
Right. Thanks, Cesar. And we have one from Hassan Khalid. It's asking about, can one stabilize the subsonic layers which we're moving?
Yes, the thing is that that's a very complex topic. And actually, I worked in something similar during my PhD thesis, because the problem is that in order to stabilize something that it's moving, first of all, you need to know how it is moving. So you need to sort of like predict its motion and then counteract it. So in an ideal world where we understand turbulence, yes, that could be the case. But in practice, that's a very, very difficult goal to achieve, right? Because basically, you need to counteract a motion which is by nature turbulent, unpredictable. Yeah.
Right. That's reasonable. Thanks a lot. And I would say we have the last one from Sadeep. He's asking about what experimental technologies are utilized at Airbus to measure the critical Mach numbers.
That's a question that I cannot anything. I mean, you mentioned Airbus, so I cannot say anything about it.
Yeah. Thanks a lot. So guys, thanks for your questions. I think we are a little bit over time. I have maybe one last slide that I would like to share with you guys and ladies. So after the webinar, we will share the content with you guys. We will share the video, so you can also watch that after the webinar. And we have also some online courses on our platform. If you're interested in learning more about CFD and CAD analysis, you can go ahead and see what we have on our website, on our platform under WiredWhite.com courses. And of course, if you have any precise, specific question to your project, to your CFD simulation, or to your project that you're working on currently, you can always go ahead and visit our WiredWhite.com members page, and you can schedule a private tutoring session with one of our tutors and course creators to work together on your particular problem or on your particular project. You can also contact Cesar if Cesar has time to work with you on your issue. That could be also an option for you to investigate and to go a little bit deeper into details into your particular project. And of course, for all of that, as a webinar attendee, you will get a discount code, WiredWhite10, where you get 10% of discount on every purchase on our platform. And with that, I would like to thank you all, especially Cesar, for giving this very interesting, insightful webinar on fluent flows, on supersonic perspectives, and giving us those insights into that aerodynamics world. Thank you so much, Cesar, and thank you so much also attendees, our WiredWhite community and members. I really enjoyed the webinar, and I will looking forward to the next one and see you guys during the next one. Thank you so much. Any final words from your side, Cesar?
No, I just hope that you have enjoyed this topic as much as I do. Please feel free to contact me like in any way to discuss more about it.
Yes, absolutely. All right, guys, ladies and gentlemen, thank you so much and have a great day, and see you during the next one. Take care.
See you. Bye-bye. Take care.
See you.